to get started. Alrighty, so good afternoon to you folks. I am Sunita, working with Dr. Barbara Chapman at the HPC Tools Group with the University of Houston. And what I thought I'll talk to you folks about is OpenMP is everywhere. Everybody is using it for lots of purposes. And my goal is to try and get it to work on an embedded board, on an embedded system. So what it really takes for OpenMP to work on an embedded system. So that's the vision of this project. And the title is Heterogeneous Multicore Embedded Systems using MCAPI, which I'll tell you in a little while what it is all about. It's again a standard interface like OpenMP put together by a bunch of industries, and I'll tell you more about it in a little bit. And this project is in collaboration with Freescale Semiconductor based off of Austin, and also funded by Semiconductor Research Corporation, SRC. So it's like a SRC and Freescale work hand in hand. SRC has a bunch of industries that work with them, and they fund universities to do these kind of research projects. Oh, come on. Okay, so that's just to give you a perspective of where embedded system is being used. All these are borrowed images from everywhere on the web. So this is the FPGA is being used to receive acoustic pings from an image. So that's sonar systems there. And this is a DSP system, which is typically used in cell towers to get, all our transmitters, all our calls and all those stuff. And then this is the NVIDIA Jetson TK1, which is used in the Audi car, it's a self-piloted car powered by NVIDIA Jetson TK1. And I think this was presented at the GTC conference early this year by NVIDIA. So you see, this is just to give you an idea where it is all being used. It's there everywhere. There are these small little devices used in lots of applications. And the main challenge is how do you program these devices? So you have those HPC systems, you have those high-level languages, high-level directives, you program them, you get results. But the embedded platforms are a little tricky. They are not the conventional IA32 kind of processors. Some embedded systems don't even have an operating system. So how do you deal with those kind of systems? And you have other devices like DSPs, you have ARM, you have FPGAs. So the problem is you try to program one particular device and you think it's going to work, your software stack is going to work on more than one device, and that's not the case. So even if you're using a device from the same family, it's like Texas Instruments, you're taking a board A, you have a program, you make it run on board A, then you have board A version 2 of the same company, and you still have a problem running your code on the device without touching it. So the problem comes when you have to rewrite your code from scratch, which means you need to understand the algorithm all over again, you need to understand the programming model all over again, and the challenging part is you need to get a hold of the architecture you're targeting. So you don't know what architecture you're targeting, you cannot program it. And when you go down the embedded level, it becomes more and more challenging, more and more difficult, because it's nothing like our desktop, right? It's got a lot of other intricate details in it. So that's the thing. So write once, reuse anywhere is not a concept that you can easily adopt for an embedded device. So you want to avoid rewriting programs from scratch, and you want to provide incremental migration path essential for application codes, and that's where OpenMP comes into picture. You insert a couple of directives, you get X number of speed up, you're like, well, I can do better. You go back and redo your directives, you plug in better directives, and it does perform well. So you want to incrementally improve the performance of your code and exploit multiple levels of parallelism, be it functional level or loop level, and with familiar commodity programming models. And like I said, there is no one universal programming model out there. There are multiple of them, and that's where the industry standards become more and more important and more crucial. So this is just a very brief idea of what's OpenMP, and I guess we all have an idea of what it is. It's an industry standard for shared memory parallel programming, supported by a large number of vendors, and Texas Instruments, there is AMD, there is Intel, Cray, NVIDIA, IBM, and so on, HP and so on. And of course, I'm sure all of you have heard about the OpenMP 4.0, which was released last year, and it supports heterogeneous systems, Xeon Phis, GPUs, and other compute devices like Texas Instruments DSPs, for instance. So this is just, and there's plenty of documentation available out there, so definitely go check it out. It's a high-level directive-based solution. It's got compiler directives, library routines, environment variables, And the simple concept that it follows is a fork join parallelism. You have a master thread and it spins a lot of threads, and then you have those worker threads doing its own job. So that's basically the fork join method. And threads communicating with shared variables, you have synchronization constructs to take care of race conditions, and structured programming to reduce likelihood of bugs. So programming is made easy because you're using a high-level directive-based programming model. So a typical OpenMP solution stack is where you have a multi-thread application. So you have an application written with using OpenMP directives, and you use a compiler that can compile an OpenMP code, and it definitely has a library, environment variables, and you have every implementation has its own runtime library, which what matters when you are talking about performance, speed up, and better execution times. And operating system followed by the platform, underlying platform. So the catch is, it's there, it's working, everything looks cool. But when you come to embedded systems, there are certain things that needs to be taken care of. As in, when I'm saying that runtime relies on low-level components like operating systems, that's not typically the case in an embedded platform because you don't even have an OS. So where do you're at a level where you don't have an operating system. A typical OpenMP implementation cannot go after a certain level. So how do you really tackle that kind of a problem? And then OpenMP has shared memory code, but embedded platforms, I'm talking about this power processor with a lot of these small specialized accelerators, and they have their own distributed memory. So how do you really, use OpenMP to target those kind of distributed systems? And vocabulary for heterogeneity is a must in embedded platforms because you have ARM DSP, you have power processor and a specialized accelerator in it, or you have an ARM and an NVIDIA GPU card. So you have these heterogeneity aspect in it. And voila, you have OpenMP 4.0. So it solves most of the problems, but I'm looking at it from an embedded point of view and not quite an HPC point of view yet. So this is what I thought I should introduce you folks to in this talk. Now that we know what's OpenMP, it's high-level directives. This is Multicore Association has put together a standard API which takes care of or which handles communication between nodes, manages resources underneath. So you have an ARM, you have say 4 ARM cores, you have 8 DSP cores, you have primitives in the resource management API that kind of queries the underlying nodes, allows you to have appropriate synchronization constructs, and also allows you to express your problem in terms of tasks. So the task concept is also similar to OpenMP tasks. However, the MCAPI, the Multicore Association task management, is more focused towards embedded platforms and not the typical platforms we are looking at. So the industries involved in this are Polycore, Mentographics, Siemens, Freescale. We are also, University of Houston is also a member of MCA. And they have more than this. Like they also have a tools API, which is also in place. But the most important APIs we concentrate on our work is the communication API, resource management, task management, and this is also something that which is the software hardware interface for multi-core, many-core. SHIM in short is also an API that was put out late last year. All right, so I thought I should go a little bit deep into the task concept because communication and resource management is something that we all use on a daily basis. And in tasks, if you look at the picture, this is something that Sven Bremer, who led the MCAPI discussions when we formulated the API, the slide is borrowed from him. So if you look at an MCAPI application, it's broken down into several tasks. And as you can see, there's more than one type of device. You have a DSP here, you have some 4 CPU cores, and you have a GPU core, and each of these devices have their own memory. So the challenge is how is the interaction going to happen between the DSPs and the CPUs and the GPUs, and how are you going to distribute your tasks among the different devices, and how are you going to interact between the memory levels of each of these devices. So the idea that MCAPI, the multi-core task management APIs have put together is somewhat like this. Each of these nodes, you could look at that as a device. So it could be a device 1, 2, and 3. And so you have a task-based application, and the application is broken down into a bunch of tasks, but there is a job associated with the task, and there are multiple actions associated with the task. The reason being, say you have a particular computation which runs on a dedicated hardware, And then from an embedded point of view, the scheduler finds out, oh, I don't have a dedicated hardware, so where do I exactly schedule my stuff? So it becomes a software-based action. So initially it was a hardware-based action. It didn't find a dedicated hardware. The action it becomes a software action. So that's why for every job you have more than one action. So this could be a hardware action, that could be a software action. The scheduler finds no hardware actions. The action becomes a software action, and you still can execute that operation, which is not the case when you don't have these hierarchies of task, job, action, which is what MCAPI was putting it together. So that's the difference between an OpenMP task and an MCAPI task, where in the latter, in the MCAPI task, you have these layers or different levels, if you like, and an OpenMP task, it's a normal task which just executes on a bunch of platforms. But an embedded, because you have these different types of hardware underneath the different memory levels, you want a step further than that. And so what we did was, our work is basically on the runtime aspect of our software stack. So at the runtime level, we tried to improve the OpenMP runtime by linking it to the MCA libraries. And in that point, we had to make some implementation choices. Like you cannot oversubscribe in an embedded platform because you have very limited number of cores given to you. You have just 16 cores. So you can only create that many number of threads, as many cores available to you. So that's where the resource management APIs from MCA come into picture, that allows you to query what you have underneath, and it only allocates those many number of threads, as many number of cores you have underneath. And so you want to avoid oversubscription, and resource management is metadata primitives to query your resources. And synchronization construct, again, there are different barrier algorithms. So you want to choose the right kind of barrier algorithm for your embedded platform. For example, say tournament algorithm might be a better one, just because you have very limited resources, very limited memory. So you do not have an option to overuse the amount of resources you have. And the memory model also, we use the resource management, shared and remote memory primitives for that. The architecture that we targeted was from Freescale, which is a power processor. It has about 4 to 8 E500MC cores. And excuse me. So if you look at the picture, you see a PME, which is the pattern matching engine, which is a specialized accelerator. And you have an SEC, which is a security engine. It's a cryptography, if I'm not wrong. So these are the two specialized accelerators, and our goal was to try and use OpenMP and MCA to target the PME and SEC of this whole architecture. So it's not a typical GPU or a Xeon Phi that we are looking at, because from an embedded point of view. So at a very preliminary level, what we did was we used an OpenMP application, and of course it's a multi-thread application. You have those directives and stuff. And we targeted the OpenMP's translation to the MCA layer underneath. So there is OpenMP, there is MCA, and the MCA layer has a vocabulary of, is there an operating system, is there no operating system, or what kind of memory do you have, is it shared memory, is it remote memory. So that's where this layer comes in. So the earlier Mickey Mouse diagram that I showed you did not have this layer. You had the runtime library and you had an operating system. So the MCA layer is the one that is sandwiched between the runtime library and the operating system, which identifies the resources of this multi-core embedded system. So the approach was, so we have our in-house compiler, OpenUH compiler, and that's, if the slides are up online, that's a link to our compiler, and it is available online for you to download in our HPC Tools website. So we used OpenACC and translated the C plus OpenMP, which is a source code, which the intermediate representation is a bunch of OpenMP runtime function calls, and PowerPC GCC of the board was used as the backend. And finally, we have the executable file linked with the object file, runtime library, as well as the MCA library. So if you look at the results, it was promising because there wasn't any overhead. And if the graphs here are, the libcomp is the proprietary GCC OpenMP runtime library, which was the one meant for the power processor board. And the libeomp is a name we have given to our OpenUH runtime, E standing for embedded. And so if you look at the enhanced OpenMP versus the proprietary runtime, EOMP versus libcomp, you see that there are not much of an overhead at all. So even if we included the MCA layer, it did not incur any kind of overhead on the overall runtime. And we also use the EPCC micro benchmarks to evaluate our runtime. So all this was done on a homogeneous processor, power processor of 8 cores. So how do you really turn this into something that will work on heterogeneous systems, which is the end goal? So again, like I mentioned, the security engine as well as a pattern matching was what we targeted. So what we did was, again, so we wanted to create some kind of a communication path between the PME and the P4080, the 8-core processor. So the next diagram is a little bit better, I guess. Yeah, so PMCI is the interface that the PME, the accelerator engine, recognizes. So the idea was to bypass that PMCI layer such that when a user comes in, he doesn't have to really navigate himself through all the PMCI low-level interfaces. So that's a low-level detail that I may not know, or I may have to study new when I look at another architecture. So the communication APIs, there are 2 types, connectionless, connection-oriented, and they help us create a layer above the PMCI, which is a lowermost layer, in the sense it abstracts the low-level layer, and you create a bridge between the PME and the P4080. So this is connectionless, so again, you don't really have the message sending and receiving, but if it was connection-oriented, you will have 2 endpoints on either side. You will send a message, the other person receives the message, and there's handshaking protocol, etc. So what we did, the lessons learned here was, it was really time consuming because A, you understand the PME first, then you understand the PMCI interface, then you need the right kind of drivers, right kind of support from the manufacturer to know all the details. So PMD does not share memory with the main processor, which is a power processor, and so we use the DMA channel to move data between both. And so yeah, this is what I was trying to say. It's really time consuming when you have to know the intricate details of the entire platform. So what we did was create this MCA wrapper via using DMA to abstract all the low level details, and that's the PMCI of the PME board in this case. And of course, the thought we had in mind was you cannot really create an MCA wrapper and just for that particular board. It has to be universally applicable to a decent extent. You can't really use it for n number of devices, but at least devices of the same type should be able to use a wrapper. So that was another challenge, coming up with a kind of generic wrapper. And the ongoing work right now is the MCAPI design is out, the APIs are out, we are creating an implementation. Siemens, which was also involved, or they were the lead in coming up with the API for task management, have also put out an open source implementation just about last month. It's available I think it's available for download. And we are also working on creating the implementation for MCAPI, which is the tasks that I was talking to you about. And goal is to evaluate an MCAPI implementation on a heterogeneous multi-core platform. And well, the preliminary results showed that when you're trying to communicate between 2 different nodes, it's always going to be time consuming unless you have lesser data transfer and an efficient communication channel. So the very preliminary implementation that we came up with is not very efficient as of now, but it runs, it compiles, we have results. But the ultimate goal would be to make sure that the time taken to communicate between 2 different nodes is reduced, which means we have to improve our implementation. And yeah, so that's what I was trying to show you, that between these 2 layers is your MCA layer. And yeah, to summarize, at University of Houston, we are trying to come up with a software stack that will be using OpenMP as a high-level directive on the top, target the translation to another industry standard, which is a Multicore Association API at the bottom, and before you go down the architecture level. So the motivation here is I don't need to learn low-level details of the architecture. Being a programmer, I must be able to use a software stack without worrying about what's underneath, but worrying about the algorithm itself and improvements to the algorithm itself. So that's the goal overall. Thank you for listening. So do you have any questions?
You have to rewrite the task management, or you use the libcomp or something like that?
I had to rewrite what again?
You have to rewrite the task management, or
not
the implementation from GCC, or...
Okay, so the question is if I had to rewrite the task implementation, or I use GCC?
The task management.
Task management. So actually, since it is not a pure OpenMP task, and we have the Multicore task API underneath, so we had to not rewrite, we had to improve the OpenMP's task runtime so that we are able to leverage MCAPI, the task management API's features. So the runtime was improved. You could say it was rewritten, but the main runtime, OpenMP runtime, exists. This is an add-on. So Multicore task management is an add-on to an already existing runtime. So it's just an enhancement. And so that's like a complete package when you want to target an embedded platform, and you don't need that extension when it is non-embedded platform. A normal task runtime should work perfect. Okay, thank you.